Hello and welcome to the 200th official video of Cornerstones of Math. In this very special video, we are going to take a look at a number 200 factorial. The problem is, how many tailing zeros are there in 200 factorial? Also, what is the rightmost non-zero digit? For example, for 20 factorial, you can see that there are 4 tailing zeros and the rightmost non-zero digit is 4. Here, we have to do this for 200 factorial. First, the number of tailing zeros. Here, the underlying mathematical principle is pretty simple. The tailing zeros occur by having a factor of 10. That is, each 10 contributes to a tailing zero. Here, 10 equals 2 times 5, so we have to look for prime factors 2 and 5. Also, it is easy to notice that prime factor 2 occurs far more frequently than prime factor 5. In other words, whenever additional 5 appears, there will always be 2 that can be paired with that 5 to make 10 and add a tailing zero. Therefore, the number of tailing zeros is equal to the number of 5s. So we have to count the number of 5s in 200 factorial. So let's count the number of 5s. Basically, we have this product. Here, the prime factor 5 appears in multiples of 5. So how many multiples of 5 are there in natural numbers from 1 to 200? Well, there are total 200 divided by 5 multiples of 5. Or more precisely, there are floor of 200 divided by 5 multiples of 5. But there are more 5s out there because of the multiples of 25, which is 5 squared. As you can see, each multiple of 5 squared contains one more 5 compared to other multiples of 5 we just saw. Therefore, we have to add the number of multiples of 5 squared to our previous result. So we have floor of 200 divided by 5 plus floor of 200 divided by 5 squared. And now you can see where this is going. Next, we have to count the number of multiples of 125, which is 5 cubed, because each multiple of 5 cubed contains one more prime factor 5 compared to the other multiples of 5 squared. So we have floor of 200 divided by 5 cubed added. 5 to the power of 4 equals 625, which is greater than 200, so we don't have to consider powers higher than 3 here. Therefore, the number of tailing zeros in 200 factorial is the sum of these 3 terms, which is 49. And we can easily generalize this result into an arbitrary natural number n. The number of tailing zeros in n factorial can be obtained by this infinite series. Alright, now the second part of the problem, the rightmost non-zero digit of 200 factorial. Method 1. Yep, for this problem, I will present you not just one, but 2 methods to find the rightmost non-zero digit. And as a matter of fact, the second method is actually simpler, more elegant, and most importantly, more general. However, this method involves the property/theorem that is not easy to come up with naturally for many people. On the contrary, the first method is the method that many people will come up with by what I would call natural thought process. So it seems more fitting to introduce this method first. The catch here is, this method requires some bashing or brute force. That is, sometimes we have no choice but to actually carry out the multiplication between certain large numbers. I will explain this in more detail when it becomes important. So the first method, but we need to introduce a new notation. In this video, when m and n have the same rightmost non-zero digit, we will denote it by writing R and D above the equality sign. Now let's get to the actual problem, and perhaps the very first thing that many people would like to try is this. Why don't we start by multiplying these 10 numbers from 1 to 10? At least it has all digits from 1 to 9, right? So let us consider this product first. First, we have 1 and 10 here. And multiplying 1 or 10 does not change the rightmost non-zero digit. Therefore, we can simply delete 1 and 10 and say that this product has the same rightmost non-zero digit as the product from 2 to 9. Next, we have 2 and 5. Multiplying them gives 10, a number that can be eliminated. So we can eliminate 2 and 5, so this has the same rightmost non-zero digit as 3 times 4 times 6 times 7 times 8 times 9. And for this product, we can do manually, but we don't have to obtain perfect answers when multiplying. For example, 3 times 4 gives 12, but for the next step, we don't have to do 12 times 6. We only have to do 2 times 6, the multiplication between rightmost non-zero digits. And we keep use this trick for the consecutive products. So in the end, we obtain the rightmost non-zero digit of 8. Alright, that was actually fairly easy. Now, let us take a look at the product of next consecutive 10 numbers, from 11 to 20. Can we do the same thing as before for these numbers? Well, not exactly in the same way. We start off similarly. Multiplying 11 does not change the rightmost non-zero digit, so we can eliminate 11 and obtain this. Now here's the first thing that's different from the previous case. We have 20 instead of 10, and unlike 10, multiplying 20 does change the rightmost non-zero digit. But we will deal with that later, so let's just leave this 20 for now. Now what about the remaining part? Surely we can do the same thing as before, right? I mean, we can just take rightmost digits, and since this 2 times 5 gives 10, they can be eliminated, so it gives something like this, which again gives this, right? Well, no. Here, the problem arises because of this sneaky 15. You see, we have eliminated this 2 and 5 because they give 10, a number with the rightmost non-zero digit of 1. But these two have actually come from 12 and 15. And guess what we obtain when we multiply these two? We get a number with the rightmost non-zero digit of 8, which means that we cannot just reduce 12 times 15 into 2 times 5. Actually, this trick of taking only rightmost non-zero digits and multiplying them does not work for the case where the number with rightmost non-zero digit of 5 is multiplied by the number with even rightmost non-zero digit. So the correct way is like this. First we eliminate 11, and let's just leave this 20 for now. Then, for this 15, we have to pair it with one of the even numbers. So let's just pair it with 12. So we write 12 times 15 at the front, then these 6 numbers, then 20. Here, for these 6 numbers, we can actually use the trick of focusing only on rightmost non-zero digits, because this product does not include the number with rightmost non-zero digit of 5, so we won't have any problematic case like this. And we have already obtained in the previous case that this product gives the rightmost non-zero digit of 8, and as for this 12 times 15, we have to carry out the actual multiplication to obtain its rightmost non-zero digit. So in the end, we obtain the rightmost non-zero digit of 8. And with this result, we are pretty much ready to tackle the case of 200 factorial. The obvious way is to think as the groups of 10 and apply the previously obtained result. And let's focus on this expression right here from the previous result. So we have this, and as for previous 10 numbers, we can write it in a similar manner. Equal R&D to 8 from these 6 numbers, and 5 is paired with 2, and remaining 10. And we can say the similar thing for next 10 numbers. The product from 21 to 30 has equal rightmost non-zero digit with 8 times 22 times 25 times 30. And for next 10 numbers, we have equal R&D with 8 times 32 times 35 times 40 and so on. And in the end, we have 191 times 192 times all the way up to 200, which has equal R&D with 8 times 192 times 195 times 200. Therefore, for the entire product, first, these 8s, and there are total 20 of them, so we have 8 to the power of 20. Next, these parts where the actual multiplication cannot be ignored, so we write the entirety of these. Finally, these parts, the multiples of 10, so we have this product. In here, first let us take a look at this 8 to the power of 20. We can find its rightmost non-zero digit using the periodic nature of the rightmost digit of 8 to the power of n, which gives 6. Next, let us take a look at this product of multiples of 10. The first thing we can do here is to divide every number with 10, because 10 does not have any effect on the rightmost natural digit. Then, we can split this product into the product from 1 to 10 and the product from 11 to 20. Here, I have already shown that the product from 1 to 10 gives the rightmost non-zero digit of 8, and the product from 11 to 20 also gives the rightmost non-zero digit of 8. So we have R&D of 8 times 8, which is 4. So now we are left with this middle part, and sadly, this is the part where bashing or brute force is required. You see, the problem with this, the number that ends with 5 times the even number pair, is that you simply cannot find its rightmost non-zero digit solely by multiplying individual rightmost non-zero digits. Therefore, for these 20 pairs, we do the actual multiplication. So for the middle part, we have the product of these 20 numbers. Now, some of you might want to proceed like this. Okay, so we have obtained these 20 numbers with brute force. Now, each of these 20 numbers has its own rightmost non-zero digit. So the next step will be taking those 20 digits and multiplying them, right? No. This is actually so wrong because of these. Among these 20 products, 2 of them have rightmost non-zero digits of 5. And we have already seen that when a number with R&D of 5 is multiplied with a number of even R&D, the situation becomes problematic. That is, if we use this 180 times 550 as an example, you can see that the product of 2 R&Ds gives the incorrect digit, and the correct digit must be obtained from actual multiplication. So what we actually have to do here is, let us pair this 550 with an even R&D number 180, and let us pair this 15,250 with another even R&D number 1,120. So we have this. And for each parenthesis, we perform another full multiplication. So now we don't have any rightmost non-zero digits of 5. Therefore, we can finally convert this into the product of R&Ds and obtain the rightmost non-zero digit of 8. Therefore, back to here, this has the same rightmost non-zero digit as 6 times 8 times 4, which has the same rightmost non-zero digit as 2. Therefore, the rightmost non-zero digit of 200 factorial is 2. Method 2. Now, in this second method, I will show you a more general way to do it. First, we have to introduce 2 lemmas. I am not going to prove them strictly, since they are pretty straightforward and the lemmas themselves are not the main point of the video at all. So the first lemma is, for 3 natural numbers a, b, and c whose rightmost non-zero digits are not 5, if a and b have the same rightmost non-zero digit, then AC and BC also have the same rightmost non-zero digit. This is pretty obvious, and actually, we have already used this lemma a bunch of times in the first method. I am just stating it here because I just want to be more formal in this method. The second lemma is also very intuitive. For natural numbers n greater than 1, the rightmost non-zero digit of n factorial is one of 2, 4, 6, or 8. Here, I will only briefly explain why lemma 2 is true. I have already explained that the number of tailing zeros is equal to the number of prime factors 5. More precisely, prime factor 5 multiplied by 2 gives additional tailing 0. Therefore, if n factorial has m tailing zeros, then n factorial can be expressed as 5 times 2 to the power of m times the remaining part that does not contain a prime factor 5, and it is this remaining part which determines the non-tailing part of n factorial. And since there are more 2's than 5's, this remaining part still contains prime factor 2, so it can be expressed in the form of 2 to the power of some natural number p times some other prime numbers. And because the 2 to the power of p times something can have rightmost non-zero digits of only 2, 4, 6, and 8, we know that the rightmost non-zero digit of n factorial is one of 2, 4, 6, or 8. Now I am going to introduce the theorem that is the main focus of this method. For natural numbers n, 5n factorial has the same rightmost non-zero digit as 2 to the power of n times n factorial. In order to prove this theorem, let us write 5n factorial in an expanded form. So we have the product of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. And the last 5 terms are 5n minus 4, 5n minus 3, 5n minus 2, 5n minus 1, and 5n. Now consider this product using groups of 5. Within each group exists at least one even number as highlighted. Using these even numbers, let us double the multiples of 5. So 5 becomes 10, and instead 2 becomes 1, 10 becomes 20, and 6 becomes 3, 15 is doubled so it becomes 30, and 12 is halved so it becomes 6, and for the last part, 5n becomes 10n, and instead this 1/2 is multiplied to one of the even numbers here. So we have this, and notice that the multiples of 5 now became multiples of 10. Here, we can divide each of these numbers by 10 using the equal R&D notation. So instead of multiples of 10, we now have consecutive natural numbers, which gives n factorial. So now we have this. Now let us take a look at each group. It is easy to find that 1 times 1 times 3 times 4 has the rightmost non-zero digit of 2, and 3 times 7 times 8 times 9 also has the rightmost non-zero digit of 2, and same goes to 11 times 6 times 13 times 14, and for the last part, we can make an educated guess that this part also has the rightmost non-zero digit of 2. I know that this is not the strictest proof, but like I said, I don't want to make this already lengthy video lengthier, so let's just move on to the next part, which is this n factorial. By lemma 2, the rightmost non-zero digit of n factorial is one of 2, 4, 6, or 8, but the actual important thing is that its rightmost non-zero digit is not 5. Therefore, by lemma 1, we can straight up multiply these rightmost non-zero digits and obtain 2 to the power of n times n factorial, which concludes the proof. Now let's use this theorem to solve the problem for 200 factorial. The obvious first step is to write 200 as 5 times 40. Therefore, by applying our theorem, it has the same rightmost non-zero digit as 2 to the power of 40 times 40 factorial. And here, we can write this 40 as 5 times 8 and apply the theorem again, which gives same R&D as 2 to the power of 40 times 2 to the power of 8 times 8 factorial. So we have 2 to the power of 48, and we can write this 8 factorial as 8 times 7 times 6 times 5 factorial. And 8 times 7 times 6 has the rightmost non-zero digit of 6, and this 5 factorial is 120, so it has rightmost non-zero digit of 2, so this entire part gives the rightmost non-zero digit of 2. And for this 2 to the power of 48, we can use the cycle of 2 to the power of 4, which is 16, which always ends in 6 in every exponentiation. So we have equal R&D to 6 times 2, which has equal R&D to 2, which is the rightmost non-zero digit of 200 factorial. And finally, this is 200 factorial. And as you can see, 49 tailing zeros, and the rightmost non-zero digit is 2. And that was all for today's video. If you're interested in this video, please go check my 100th video on this channel, where I have calculated the least common multiple of all natural numbers from 1 to 100. Also, please don't forget to subscribe to my channel, and I will see you in another video.